All right, welcome back to another explainer. Today we're going on a wild ride that spans two entirely different scales of engineering. We're kicking things off right in the macro world of manufacturing, looking at exactly how physical circuit boards are put together on the factory floor. Then we're going to shrink all the way down to the microscopic logic of data storage to understand the tiny brains that manage our digital lives. It's a brilliant story of absolute precision, so get comfortable and let's jump right in. Here's our roadmap for the day. Assembling the circuit board, meet the flash controller, reading, writing, and erasing, digital housekeeping and lifespan, and finally, the future of storage. Let's get to it. Section 1. Assembling the circuit board. So we're starting right on the factory floor to really understand surface mount technology, or SMT. The whole game here is slashing production costs without ever sacrificing a drop of performance. It's like a highly choreographed dance. Step 1 is solder paste printing. You've got to apply the exact right amount of paste onto the pads. Your scraping angle, the speed, everything has to be totally perfect. Actually, the paste even has to be temperature controlled beforehand. Then, step 2 is chip mounting. Picture high-speed mounters aggressively but accurately slapping down tiny components, while slower, multifunction mounters take their time to carefully align the big, complex stuff, like your ICs and BGAs. Finally, step 3, reflow soldering. The whole board gets shoved into an oven to literally bake it all together into a solid foundation.
Now, check out this number, 217 degrees Celsius. That is the exact melting point for your industry-standard lead-free SAC305 solder paste. When that board is in the reflow oven, it's not just getting cranked up to hot. The oven's thermal profile has to meticulously cross that 217-degree threshold to actually melt the paste and form a solid connection. But, and this is a huge but, it absolutely cannot hit 250 degrees or else you're going to completely fry those delicate little components. Talk about a thermal tightrope. So after it's baked, we need some serious multi-layered quality control to make sure this thing actually works before a consumer ever touches it. First up, SPI catches any early paste defects. Then AOI comes in, that's automated optical inspection, using optics to spot missing or tilted parts. Fun fact, those tilted parts are often called tombstones in the biz. But what about the hidden connections buried deep under the chips? Well, that's where AXI uses automated X-rays to peer inside. And to top it off, ICT physically probes the circuit to make sure there is zero electrical shorts. It's an absolute gauntlet of testing. All right, so we've built this physically perfect circuit board, survived all the intense inspections. But that brings us to a massive question. What exactly happens inside those highly complex memory chips we just permanently welded to the board? We've mastered the macro factory floor, so now let's zoom way, way down to the micro level of our data. Section 2. Meet the flash controller. We are shrinking down to poke around inside the flash memory controller. Think of this specialized integrated circuit as the literal brain of your SSDs, your thumb drives, your SD cards, the whole shebang. Because here's the thing, without a controller translating your host commands, raw flash memory would be pure, unusable chaos. NAND flash doesn't behave like your old-school spinning hard drives. It plays by incredibly strict physical rules. So the controller steps in, sitting right between your computer and the raw memory dies. It uses its own ARM-based processor, its own RAM, and its own firmware, just to make sense of the mess and keep your data perfectly intact. Just look at this staggering evolution. We start way back in 1984, when Toshiba's Fujio Masuoka first dreamt up the flash concept. Fast forward to 1991, and SanDisk hits the market with a 20-megabyte card running on early BASIC controllers. Skip ahead to 2011, and boom, the NVMe protocol changes the entire game by directly tapping into ultra-fast PCIe lanes. And now, looking at 2025, we're seeing chips like the Phison E28 literally integrating built-in AI processing to handle massive server workloads. Honestly, it's a mind-blowing leap in processing power. Section 3. Reading, writing, and erasing. So now that we know what this brain is, let's talk about the physical gymnastics it has to perform just to save or delete a simple text file. This is one of the craziest quirks of flash memory. You can write data super fast in these small little chunks called pages, taking maybe 200 to 500 microseconds. But erasing is a whole different beast. You can't just erase a single page. Nope. You have to wipe data in massive chunks called blocks. And to do that, the controller has to blast the block with a huge hit of negative voltage. We're talking negative 15 to negative 22 volts, just to clear all those cells out simultaneously using quantum tunneling.
And because of this ultra-strict block erasing rule, you face a huge fundamental limitation. You absolutely cannot overwrite an old file with a new one in the exact same physical spot. No in-place overwrites, period. Instead, the controller has to play this crazy game of musical chairs. It reads the valid data you actually want to keep, copies it over to a brand new, empty page somewhere else entirely, and only then can it trigger that massive voltage spike to nuke the old block. Which brings us to incremental step pulse programming, or ISPP. When the controller is writing data, it's literally painstakingly nudging individual electrons into place. It hits the cell with a tiny voltage pulse, stops, and checks the voltage level. Then it pulses again, checks again. It's constantly verifying its own work so it doesn't accidentally overshoot and flip the wrong bit. This kind of insane iterative precision is the only way we can pull off modern multi-level cells that cram multiple bits into one single microscopic location. Section 4. Digital housekeeping and lifespan. Now, because the controller is endlessly shuffling data around to dodge that block erase rule we just talked about, it has to do a ton of background digital housekeeping. If it didn't, the drive would quite literally eat itself alive. See, flash cells physically degrade every single time you erase them. So, to combat this, the controller uses an algorithm called wear leveling. It actively watches the age of every single block and strategically moves your static, unchanging data, like your OS files, all around the drive. Why? Just to force the entire physical drive to age at the exact same rate, keeping any single block from getting burned out too fast. And wear leveling is not just some nice-to-have bonus feature. It is life or death for these drives. Back in the day, older single-level cell NAND could handle around 100,000 erase cycles before dying. But today, we all use triple-level cell, or TLC NAND, because it holds drastically more data. The catch? It is incredibly fragile. We're talking maybe 1,000 erase cycles before it kicks the bucket. Without the controller expertly balancing that wear and tear, your shiny new SSD would fail so incredibly fast. So, to keep free space open, the controller runs a process called garbage collection. It's exactly what it sounds like. Think of it like trying to declutter a really messy room. The controller finds a block that's this ugly mix of valid files and deleted trash. It grabs the few good files you actually want, packs them safely into a brand new, clean box, and then bam, tosses the entire old, messy room right into the incinerator. And the best part? It quietly does all of this in the background while your drive is idle so your computer doesn't randomly freeze up while you're working. All of this chaotic data movement relies on the flash translation layer, which is basically the internal GPS map of the drive. Now, engineers have to pick a mapping scheme, and it's a huge trade-off. Page-level mapping tracks every single tiny piece of data. It's lightning fast for random access, but it gobbles up massive amounts of RAM just to store the map. Block-level mapping, on the other hand, tracks data in huge chunks. It keeps the memory footprint super low, saving money, but it heavily slows down random writes because you have to rewrite entire blocks for a tiny change. So modern controllers, they usually run super clever hybrid systems to try and get the best of both worlds.
Section 5. The future of storage.
All right, let's look at where we're headed, because flash controllers are evolving fast to handle the downright mind-boggling scale of tomorrow's computing. 14. That's 14 gigabytes per second. That is the sequential read throughput we're seeing on cutting-edge PCIe 5.0 SSDs dropping in 2025. To actually hit speeds that insane, the controller is doing some heavy lifting. It's interleaving operations across dozens of channels, reading from multiple memory chips all at once, and correcting bit errors on the fly. It's literally a symphony of parallel processing. And we aren't just getting faster, right? We're getting way smarter. The controllers of tomorrow are packing onboard neural networks to predict their own wear patterns before they even happen. They are being engineered to manage these impossibly tall 430-layer 3D memory stacks expected around 2026. We're talking new CXL interfaces, pooling entire terabytes of memory for data centers. They're even baking post-quantum cryptography algorithms straight into the silicon to defend your data against future quantum computer attacks. I mean, no way, right? I want to leave you with one final thought to chew on today. We started out on a macro factory floor looking at baking solder paste, and we ended up down in the weeds with AI-driven, quantum-defending microbrains. So, as these controllers become more and more autonomous, predicting their own physical wear, will our digital memory managers soon completely outsmart the very manufacturing processes that built them? It's a pretty wild thought. I really hope this explainer completely transformed how you look at the incredible hardware sitting inside the devices you use every single day. Thanks so much for hanging out with me, and I'll catch you next time.